Good afternoon, and thank you for joining us this afternoon. Today we talk about some measurements that we obtain by Doppler and how we use them to derive flow and estimate pressure gradients. We'll start with some principles that many of you know, may have forgotten, related to basic definitions of force, pressure, how that relates to flow. So instead of thinking of solid objects moving, we have to treat the fluid as the object of interest and see how we look at it. So the basic definition of pressure is a force per unit area. And because we talk a lot about units, and we'll have a brief presentation about how we get to the units that you frequently use and why, for example, we see the 4v squared expression. So the units of force in the SI system are either dynes per centimeter squared or Newton per meter squared. 1 Newton per meter squared is 1 Pascal. If we want to sort of get to another look of pressure, because say we will not be measuring force, so we can remove force and use Newton's second law and say force is mass times acceleration divided by area. We do not measure mass, but we are more into measuring volume, and therefore we remove mass and we put in its place density times volume. And because volume can be looked at as dimension cubed, and we are dividing by area, which is dimension squared, that reduces to this basic expression of pressure. Product of density, acceleration, and distance. If we think of fluid, say in a tube above the ground, vertical tube, not with any angle to the horizontal, and we say we are interested in knowing what is the pressure exerted by 1 centimeters of water, we put that H at 1 centimeter or 0.01 meters. And we have G either in meter per second squared or centimeter per second squared units, and then the density of water is 1. So you see that 1 centimeter of water exerts 980 dynes per centimeter squared. Mercury, which has a higher density, 1 millimeter of mercury exerts, because of that higher density, much more pressure. And frequently we are looking at blood height, for example, jugular venous pressure, and we are interested in saying what is the pressure, say, in the heart in millimeters mercury instead of just centimeters of water. So if you look at that expression, you would see that 1 centimeter of water exerts 0.74 millimeters of mercury. So these are some basic things we went through. Let us look at flow. To quantify flow, we can look or simplify it by saying we are looking at blood, because that's what we're interested in, as opposed to any fluid that is going through a cylinder. The cylinder has a cross-section of being a circle, and so the flow is given by the product of area and velocity. You can see, based on the units, that this would come into volume per second or dimension cubed per second. To get the area of a circle, we do the pi r squared. If you say it's not a circle, it's an ellipse, and in many situations it's more of an ellipse, and not infrequent, it's neither a circle, not an ellipse, and then we need more complex expressions to characterize these cross sections, but the basic ones are the circle or the ellipse. For the ellipse, to capture the area, you want to get the minor diameter and the longer diameter, and then you divide that by 2, and that's the expression we rely on. So it simplifies to, if I can measure the diameter and I can measure the velocity, then I can get at flow. Flow in a tube. If there is free moving fluid and that fluid is going to go through a tube, the layers of fluid, we can think of fluid as several concentric layers, one on top of the other. The layer of fluid that makes contact with the wall of the tube, the edges of the tube, will end up no motion. And as we go from that, the outer edge of the tube, towards the center, the velocity keeps increasing, and the highest velocity is in the center. When the full flow pattern is realized, it's parabolic in shape, as you see here. Now, when we think of flow or we think of motion, we think of something that opposes the motion. So for fluids, what opposes the motion instead of friction is viscosity. And fluids that have a higher viscosity face higher frictional forces. In essence, these layers, are they freely sliding one on top of the other, or there is some resistance for that motion of the fluid? Blood is spoken of as a Newtonian fluid, and what that simply means is that the shear tension and the velocity gradient are directly related to one another. The higher the tension, the greater that you see the velocity changing over a certain vertical height. And so if we go to that concept of relating the stress per unit area, which would have the same units as pressure, and velocity gradient, remember the gradient here of the velocity is a change over a certain height, so it's with respect to distance, not to time. We can say that the shear tension is directly related to that velocity gradient, and the constant is the viscosity. So if you rearrange and ask the question, what are the units of viscosity? It has it has the units of pressure up there, so that's the Pascal, and then distance over velocity. So if you do that sort of division, you end up with the units of the viscosity being the Pascal second product. Now let us take it a step further and look at flow in a rigid tube. The model of looking at flow in a rigid tube is not directly applicable to flow, say, in a blood vessel or within the different chambers of the heart. But it helps us look at some variables that still apply, and perhaps as opposed to absolute values, we are looking more into trends that we can gain from looking at these relations. So if you look at the flow across the tube, there has to be a higher pressure at point 1 compared to pressure at point 2 for flow to go from 1 to 2. We say that the length of the tube is given by L, and then we say that the radius of that cross section, which we assume is going to be a circle, is given by A. But if you were to go at different concentric layers of the fluid, as we were talking earlier, the radius for each of these layers, because you will see we are interested in deriving a relation that characterizes the flow in different cross sections as well, can be given by a radius of R. It's just noted the velocity is 0 at the edge where the fluid comes in contact with the wall of the tube and is highest in the center. In between, the velocity will gradually increase. What is the factor that is limiting the flow? It is the friction. And so at equilibrium, the pressure force, if you would, that is trying to get flow from point 1 to point 2 is being resisted by the friction force. That's the derivation for the Poiseuille's law, but it is basically going back to that last slide and saying what is pressure force and what is friction force, and that's the expression for each of these. I will not dwell on that expression much, except to notice that at the center, where now we don't have any vertical radius, the velocity, which is the maximum velocity for that fluid, is directly related to the pressure gradient. Makes sense. Is inversely related to the factors that slow the flow. What are the factors that slow the flow? The viscosity and the length of that tube over which it is facing the resistance. But it is directly related to the radius. The larger the radius, the higher the velocity. So moving from velocity to flow, we can replace the velocity no longer in the center. We are now looking at what we call a mean velocity for that cross section. It can be shown with reasonable derivation that mean velocity is about half the maximum velocity. So we do this change from maximum to mean, and we use the area expression, pi a squared for the radius, and then you end up with that classic equation showing that flow is directly related to the fourth power of the radius, the pressure gradient inversely related to the length and the viscosity. If we think in terms of resistance, then the resistance offered to the flow is greater in a longer vessel when you are looking at more viscid fluids and in smaller tubes. Because of that fourth power, you can appreciate that this cross-section radius will have a dominant effect when you produce about equal percent changes in each of these variables. Okay, we are there. So now let us take that Poiseuille's law and say, how does it apply to flow in blood vessels? So there are some assumptions that went into that expression. The first assumption is that the viscosity is not different in relation to the size of the vessel. The truth is, if you look at very small vessels, less than 0.5 to 1 millimeters, which we do not see by Doppler, the proportion of red cells to plasma is different, and so the viscosity is different. We are assuming that the flow is laminar flow, and in normal hearts, except for a very short distance in the pulmonary artery and the aorta as the flow gets up, it is indeed laminar. A big assumption is circular cross-section that can be dealt with mathematically if you know what the shape, what the cross-section looks like. But another thing is, it is not infrequent that you see vessels changing in diameter as you progress along the length of that vessel, and so a single cross-sectional assumption does not apply to the whole vessel necessarily. One of the largest errors comes from the assumption that we are looking at inelastic tubes, which is a rigid tube in the equation we just looked at. As blood is forced into this vessel, or as blood goes into a vessel, the artery can expand, and so that diameter changes dependent on the flow rate. And that introduces an error of at least 10% if you want to go and sort of quantify absolute flow just based on the variables you are provided with, as opposed to directly measuring it, say. Another assumption that Poiseuille's law makes is that the flow is steady flow. It is not changing, as we know that flow through the cardiovascular system is pulsatile with varying velocity profile. But if you say, let me look at an average of the flow, how it's going through X amount of time that is present in systole, and you want to use mean values, that can give you some approximation of what the true flow may be. So we go back and we look at another, what you can say, a physical expression of the likelihood of whether laminar flow will be maintained or we will be looking at turbulent flow. We look at Reynolds number. That's a number that has no units. And so it's a balance, or it's a ratio of inertial forces to viscous forces. If there are more inertial forces, it is easier to get into turbulent flow. The viscous forces are the forces that are preventing this from happening. So if you ask the question, what surrogates or what things can we look in place of inertial forces, the inertia is related to the mass of the object and if it is moving to its speed. And so the mass is represented here by density, the velocity we just said, that's part of the variables that we think of when we look at moving fluid, and then the diameter is a surrogate of flow. And then viscosity in the denominator. And then you remove density and put in its place mass over volume, and you still have the velocity and diameter. So you can reduce that or change that numerator one more time and remove mass and put in its place force over acceleration. When you reduce this, you will end up with Pascal second units. And then you have in the denominator also the units of viscosity, which is Pascal second, and that's why this is dimensionless. We already covered the flow and how we do it. Let's think more critically at what are the potential errors in calculating flow. So one error is I make a diameter measurement that is erroneous. Say the diameter is 2.5 and I measure it 2.2 or 2.7, whatever it is. So that's an obvious error. Another error comes from geometric assumption. I'm assuming it's a circle when it is an ellipse, for example. Then comes the issue of phasic flow and instantaneous area. In some places of the heart, for example, if you look at flow through the RV outflow tract, the instantaneous area has been shown to vary with flow. Absolute flow and changes in area, we make use of that, for example, in cases of aortic stenosis, where we are asking the question, is this valve having a small area because of less flow? And if we force more flow, the area will be larger. And then because we are combining two measurements to calculate flow, is the diameter measurement done at the same location where the velocity measurement is obtained or not? Finally, nowadays it is possible to do that, but previously also there was interest in bypassing this diameter and circular assumption or geometric assumption and saying, let me measure the area by planimetry. That's a way of bypassing the geometric assumption. Of course, that comes again with its own error. I measure the area or I trace the area incorrectly. That will translate to errors in the area and errors in the flow. So most of the errors that come in flow calculations are coming from errors in area measurements. A frequent question that comes to mind is, how does an error in the diameter translate to an error in the area? Many people at first think about it and say the diameter or the radius is squared, and so the error is squared. It is not. That's sort of basic algebra, like middle school algebra, showing how the relation between the error in the area to the error in the diameter. It's twice the error. So a 10% error in diameter translates to a 20% error in the area. Not to minimize it, but you can see that the more the error in the diameter, the worse the error in the final flow calculation. So flow is area and velocity. We covered the errors in the area measurement. How about the errors in velocity measurement? One assumption is that the velocity in 3D is the same. So it doesn't matter where I measure it. In some cases that's okay, it's a reasonable approximation. In some cases it is not. So if you were able to get the true vector, that's what you want to enter. We need to look at the appropriate component of the spectral profile. What does that mean? What it means is there are red blood cells that are moving with different speeds. Some will have a highest speed, some will have a lowest speed, and then the bulk of the cells will be moving with a speed in between these highest and lowest. That's the speed you should measure. It is called modal velocity. The way you recognize it is by getting the brightest signal, of course with careful adjustment of gain. We talked about 3D spatial velocity vectors, the signal strength. Sometimes when someone is on mechanical ventilation, the Doppler signal that you get is faint. And when the signal is faint, then I don't see where the peak value is exactly.
It's not coming off. It's not coming off. I was trying to put the power off.
Okay. We don't see where it is exactly, and so I trace it incorrectly. One possibility for someone who's being scanned, for example, while on mechanical ventilation, instead of me just capturing 3 beats, the ventilator goes through phases. So there is the phase when it is pushing air into the lungs with inspiration. That's when my signal will not be bright. I just record for a longer time period, and now I will catch the phase when that push of air is no longer present, so the signal will increase its brightness. The issue of non-simultaneous measurements of area and velocity comes into play because they are not recorded in the same plane, if you would. Not in all cases, but I'll give you the clearest example. When we measure the left ventricle outflow tract diameter, we measure it in the paralong view. When we measure the velocity or the time velocity integral through the LV outflow tract, we take it in the apical views, apical 3 or apical 5. So it is not simultaneous. If someone is in regular sinus rhythm, not an issue. But if someone is having a lot of ectopy or atrial fibrillation, this can cause problems. And then the assumption of continuity, what does that mean? What it means is if I measure the flow, say, through the LV outflow tract, it is the same as, say, the flow in the root of the aorta. It is true, but if I go above the root of the aorta after the coronary flow has taken off, then that assumption is not necessarily correct. It's not a huge error, but it is not the absolute same flow that you get through the LV outflow tract. If we can calculate stroke volume, then we are on our way with the heart rate to get cardiac output. And so to get stroke volume, we need cross-sectional area. And instead of just velocity, velocity would get you flow in centimeters cubed, say, per second. I am interested here in absolute volume. And so we do something called velocity time integral. And that would have the units of centimeters. And now you end up with the absolute flow. You multiply that with heart rate, you get cardiac output. In the older days, something we do not do nowadays, if you look at, say, flow through the LV outflow tract, it looks like a triangle, and if I do not want to do the actual tracing, I look at the triangle and I say, what's the area of the triangle? So half base times height. The base here is on the time axis, and the height is on the velocity axis. This calculation of cardiac output has been put into good use over the years. For example, drug therapy, somebody who's in heart failure, reduced EF, small stroke volume, and they are giving them inotropes. You can administer these and then see what happens to the stroke volume. You can look at different pacing modes, variable interventricular time delays, variable AV delays, and you see how that affects the cardiac output. You can study changes during physiologic states like pregnancy, labor, and postpartum. You can look at flows in fetuses and in neonates, and later on as the child grows. You can look at what happens to the flow with Doppler, and this is of particular interest. Particular interest in looking at, say, regurgitant lesions, particular interest in looking at patients with heart failure preserved EF, because many of these patients have a smaller increment in their cardiac output relative to the change in the pressure, and that would allow you a look at this. Flow calculations are needed if you're going to quantify shunts, you're going to quantify regurgitant volumes. We'll go through these in detail, and flow calculations, and as well ejection fraction. So how do we calculate flow through the LV outflow tract? We go to the paralong, we zoom. The reason we want to zoom is to minimize the error. And now I have the diameter, and that's the time velocity integral here, the product of velocity and time. And then you go and you assume the circular cross-section for the LV outflow tract. You multiply it by that, you have flow through the LVOT. We can also get flow through the RV outflow tract. So this is something that you would need, for example, for shunt calculations. And you can also use it to look at regurgitant lesions, as you will see some examples. So you can get the pulmonary artery long axis view. You can also do parasternal short axis view at the level of the base of the heart. You visualize the pulmonic valve. You can put color to see the edge of the RV outflow tract. And again, we go for the time velocity integral. Notice that there is the brightest part, that's the modal velocity we were talking about. Sometimes you will see fainter signals with higher velocities. We do not go for these when we do time velocity integral measurements. Mitral inflow is recorded at two levels. At the level of the annulus, that's the signal that we want to acquire if we are going to rely on mitral inflow to assess mitral valve regurgitation, for example, or aortic valve regurgitation. And then we go at the tips. The reason we go for the tips is for the diastolic function measurements, but not for flow. So we have to acquire signals at both levels. And whoever is scanning needs to show where their sample volume is and needs to look critically. Did I put it really at the tips, or I'm still in the funnel of the mitral valve? There can be major differences, for example, in some of these measurements based on that location. Includes the peak velocities, includes time intervals. So the concept of using flow to quantify MR is shown on that slide. That's sort of the basic concept. If you think of the stroke volume, when the ventricular volume decreases from end diastole to end systole, some of that flow will go through the aortic valve into the aorta, into the systemic circulation, and some of that flow will go back into the mitral valve. And so if I know the stroke volume and subtract from that the aortic flow, then I have the mitral regurgitant volume. Example from a patient with a flailed segment, a lot of color here, filling the atrium, so it's not an inconsequential lesion. Let's see how we go about quantifying that. So we get the mitral annulus diameter, we get the mitral annulus flow, we go through the LV outflow tract diameter, and we get the time velocity integral through the LV outflow tract. And then we say, these are the numbers. So there is the flow through the mitral valve, 113 milliliters. Flow through the aortic valve is less, 42 milliliters, because not all of these 113 mLs that the ventricle ejects ends up going through the aorta. The difference between them is the mitral regurgitant volume. And if we express that in the numerator of a ratio where the denominator is the total stroke volume, we end up with a regurgitant fraction. Yes, we do these calculations, and the more you do it and the more careful you are with signal acquisition and which beats to analyze, you will get better at it. But even for someone who, say, doesn't go through that exercise, the actual values provide you with a lot of insight. How? I'm not going to pay attention to any of that stuff. I will see a ventricle that is large in size, ejection fraction normal, and then I look at a good signal through the LV outflow tract, and the normal time velocity integrals should be in the 20s, should be higher, larger in larger ventricles, unless the diameter is larger, in which case the TDI doesn't get much increased. But here this is a large ventricle with good EF, and I'm having a time velocity integral of 11 centimeters. So that should catch my attention as well. Let's look at aortic regurgitation. This is a patient with a dilated root, some eccentric aortic regurg, and we do the same exercise, flow through the LV outflow tract 82, flow through the RV outflow tract 54, and now we have a regurgitant volume, the difference between them of 28, and we can express that as a regurgitant fraction. So done with flows. Let's talk about energy, pressure, the relations to flow, and where we take it from here. Again, we'll start with some basic definitions so you are familiar with the expressions that are being used. Energy is simply defined as the capacity to do work. We can go to the basics, and we'll start with, say, a solid object moving. Work is given as the product of force and distance. We are talking in terms of pressure, so I can remove force and say work is the product of pressure, area, and distance. Okay, distance multiplied by area is volume. And so now work is given by the product of pressure and volume. which means if I have pressure and volume relations in a given ventricle, left or right, I can calculate the work that this ventricle does. And now we have non-invasive tools to allow us to calculate that as well. Let's look at another expression for obtaining work. If we go back to this one and say we remove force and put in its place the product of mass and acceleration, that's Newton's second law, and distance, we can see, and then we remove acceleration and say it's change of velocity over a period of time, we can see that work can also be expressed as the velocity squared, and we remove mass and we say density and volume. So that's kinetic energy, and that's something that we think about and make use of, as you will see, in obtaining pressure gradients. Lastly, work for a fluid that is, say, stagnant above the horizontal level or above the center of gravity of the Earth is given by that basic expression, mass times free fall acceleration, since this fluid is not moving, multiplied by the vertical height. And so again, if I know the density, I know that vertical height, and this is a constant, the free fall acceleration, 9.8 meters per second squared, then we can obtain potential energy. And a fluid that is in motion, by virtue of its position above the center of gravity, by virtue of its motion, will have the kinetic and potential energy components, if you think about it. We'll touch bases now with another expression that we need to obtain estimates of pressure gradients, and that's Bernoulli's law. Before we get into that, many of you use the continuity or have used the continuity equation. Where does that come from? If we look at flow through this arrangement of tubes, flow goes from point 1 to point 2. All of the flow goes from point 1 to point 2. And therefore, flow at point 1 is equal to flow at point 2. And we replace flow by area and velocity at point 1, area and velocity at point 2. It follows that if I'm interested in the area at point 2, then I can divide area at point 1, velocity point 1 by velocity in point 2, and now we have the area. Okay. Things that follow as well from that expression is if the energy is constant, and it is, we are going to ignore frictional losses for now, then the place where the velocity is higher, the kinetic energy proportion contribution to the total energy is higher in that narrower cross-section. That's the full expression for the energy at points 1 and at points 2. And with the conservation of energy, we would say that energy at point 1 and energy at point 2 are equal. If we assume that the amount of flow, the absolute volume is sort of the same across, then we can remove that from the expression, and it simplifies to pressure plus kinetic plus horizontal, plus energy at point 1 and the same at point 2. Since the vertical height above the center of gravity is the same, we cancel these potential energy components. And so we end up with the sum of pressure and kinetic energy point 1 equals sum of pressure kinetic energy at point 2. We rearrange because we are interested in this pressure gradient estimation, and that's what you get. If the velocity at point 2 is so much higher than the velocity at point 1, you can ignore the velocity at point 1. And now we end up with that expression. The pressure gradient between points 1 and 2 is given by half multiplied by the density of the fluid multiplied by the velocity at point 2 squared. Okay, we measure velocity in meters per second. We are frequently interested in getting pressure estimates not in Pascal units but millimeters mercury. That shows you how we end up with the 4v squared expression. Basically, you use the units, converting them from centimeters per second, or use the velocity in centimeters per second that you measure, you make it meters per second. You try to change the pressure would change the pressure actually. You can do that with these expressions, knowing what 1 millimeter mercury exerts. And then with some rearrangement of terms here, you end up with the 4V squared. But it is an approximation, as you see. And a big part of this approximation is we ignored the V1, the velocity proximal to where the point 2 velocity is taking place, and we've also ignored frictional losses, and we've ignored inertia. And that's what this slide shows. So that's the expression that we arrived at 2 slides ago. That's the inertial term, and that's the viscous losses. It is reasonable, if you're looking in a normal heart, to ignore the inertial term. And thus, we can of course ignore still that frictional losses. Obviously not perfect, but that's a reasonable approximation. I'll show you that this approximation does well. The only situation where we want to go back and put V1 here is if the V1 is at least 1.5 meters per second. So example, you are looking at somebody who has serial obstruction, subaortic membrane and aortic valve stenosis, dynamic obstruction and aortic valve stenosis. If we are interested in the gradient across the aortic valve, I cannot just go through the peak velocity through the aortic valve and say it is 4V, that velocity squared. I have to enter the V1. So that expression, that 4V squared, has been used for many purposes. PA pressures, gradients across stenotic valves, prosthetic valves, intracavitary gradients, looking at rate of pressure changes during systole and diastole for both ventricles. Can estimate left ventricular end diastolic pressure and left atrial pressure. In the first case, we rely on the AR jet, in the second on the MR jet. It's not perfect, but I will highlight applications that are accurate and that are used day to day. So PA systolic pressure, we all rely on the tricuspid valve. We try to get the peak velocity from multiple windows. We get a complete signal as much as we can. And then we apply that modified Bernoulli, and we say the pressure gradient between the right ventricle and the right atrium is 4V squared. We remove this TR velocity that we measure. And then we say RV systolic pressure is the 4V squared plus right atrial pressure. Most patients, of course, there are patients with congenital heart disease that can have pulmonic stenosis. But in the absence of pulmonic stenosis, the pressure in the right ventricle is the same as the pressure in the pulmonary artery. When you have good alignments and complete jets, we do a good job in getting reliable estimates of PA systolic pressure. With incomplete jets, it's a different story. We can also look at PA diastolic pressures and PA mean pressures. So the PA end diastolic velocity reflects the difference between the pulmonary artery diastolic pressure and the right ventricular end diastolic pressure. Again, we make an assumption that the end diastolic pressure in the ventricle is the same as the right atrial pressure. Is not the perfect assumption, if you would, across the board, but for now it may be reasonable to think this way. Then we can say that the PA diastolic pressure is given by 4 end diastolic velocity squared plus right atrial pressure. So now we have PA systolic, we have PA diastolic. Example of aortic stenosis. This is a jet from the suprasternal notch, and you can appreciate that the peak is hovering around the 4s. Of course, we try to get the jet from multiple windows, and there will be in-depth analysis of how to do that with the aortic stenosis discussion. Mitral stenosis jets, we can get very good, almost perfect alignments from the apical windows. And of course, if you have that, then you have peak gradients and mean gradients across a stenotic mitral valve. That's a recording showing the Doppler gradients and the LV-LA pressure gradients from a patient with a mitral Hancock prosthesis. That's an old prosthesis. And the beauty of this illustration is the AFib and the varying RR intervals. So as you expect with shorter RR intervals, The gradients are different than with longer RR intervals. Take a look at the mean gradient by cath 10 and by echo Doppler 10. The gradient here mean 14 and the same by echo. And you can go on beat by beat, a very faithful reproduction of the true gradient. Dynamic gradients are looked at. Of course, there is interest in knowing where it is present. That's a separate topic to talk about, but we can apply the modified Bernoulli equation here and say 4v squared, 4 multiplied by 36 gets you the number that you see here. We can look at the rate of rise of pressure in the ventricle relying on the mitral regurgitation jet. And so we choose 2 points. One point where the peak velocity is 1 meter per second and another point where the peak velocity is 3 meters per second. That 1 meter per second by the modified Bernoulli equation translates to 4 millimeters mercury and the 3 translates to 36. So the difference between them is 32 millimeters mercury. The pressure has increased by 32 millimeters mercury between points 1 and point 2. If I divide that by the time interval between these 2 points, then I have a dp dt. And in this case, is reduced markedly for 82 millimeters per second. These have been looked at mostly in research settings, but we do not use it in day-to-day applications. Having said that, the shape of the MR signal, how fast it rises, can give you an indication of how fast the pressure is rising in the ventricle. The big factor that we are ignoring in this is that the change in pressure is assumed to be entirely due to what is happening in the LV pressure. It is a pressure gradient, and therefore how the left atrium is behaving during the course of systole in terms of its pressure is another variable if one wants to look at all the components of this expression. You can do the same for the TR, and I'm illustrating here 2 hearts. This is a normal heart. You can see a faster rise in pressure, and this is a diseased heart, a slower rise in pressure. You can also look at the rate of pressure decline. Here negative dp dt, and you can see it's in that normal heart, it's descending faster, much faster than that diseased heart. The last application I'll touch on is using the AR jet for estimation of LV and diastolic pressure. So we measure the blood pressure, and we make the assumption that the pressure that is measured in the brachial artery is the same as the pressure in the root of the aorta. It's a big assumption, but that's what we start with. And then we go through the exercise and we say the end diastolic velocity, the 4v squared part for us, is the difference between diastolic pressure and end in the aorta and the left ventricular end diastolic pressure. If I know the end diastolic velocity, 3.6, then I put it in here and I rearrange that and I end up with a calculation showing an ADP of 18. The big assumptions in this expression are the aortic root pressure being the same as a blood pressure that is measured, say, in the brachial artery. Another big concern for this part is how well aligned we are with the AR jet. And notice there can be significant errors because the error in the velocity will end up being squared as well. So I'm going to stop here and take questions. Okay. Thank you all for questions. Okay.
So in the absence of TR, how we evaluate RVSB?
Okay. So if we have a pulmonary regurgitation jet, that would be helpful. So let me explain. First, before we leave, if we do not have TR, if a case is being scanned with the objective, I want PA pressures, that's why I'm sending the patient to be agitated saline. If I use ultrasound enhancing agents to look at the endocardial border, I have to go back and look at the TR and try to acquire it from multiple windows before giving up. Now, I did my best and I don't have a TR, but luckily I have a PR, pulmonary regurgitation. The end diastolic velocity will give you an estimate for the pulmonary artery diastolic pressure. If you have a complete envelope and you have the peak velocity, I didn't touch on that, but you can get the diastolic pressure. But this is a calculation approach to get the mean PA to accelerate through the RV time, and at that hypertension is really the mean pressure, not the PA. Reliable estimate of. Okay. Yes.
In what situation the mean RA pressure does not equal RV EDP?
So if there is RV diastolic dysfunction, similar to the left ventricle side, the RV and diastolic pressure could be higher than the mean RA pressure. In general, unless we're looking at extremes, the difference will not be large, and therefore it is not unreasonable to use RA pressure estimates that you get by other means. Okay. Thank you all.